So welcome to the 6-7 notes where we're kind of taking a break from talking about proportions ratio. I mean, it will factor in, but we're jumping forward because I want to connect what we did in chapter 9. Remember, we talked about different transformations, and we talked about rotations, reflections, dilations, and so how does that factor into similarity? So if you remember, let's just write down what are the different types of transformations. Sorry, I'm just going to kind of borrow this space right here. We had translations where you took a figure and you just slid it over here. We had reflections, okay, where you have this triangle and like you have a line and you reflect it over that line. Then we had rotations, okay, where you had this figure here, you had a point and you would rotate it however many degrees, so like this would be the new rotation. And finally we had dilations, where you had a figure, you had a point, and then you would kind of dilate it, so you would enlarge it or reduce it. So these were chapter 9. These were our different transformations. So if you remember that keyword isometry, and isometry means the before and after is congruent. And let me just jump over to GeoGebra here. By the way, if you hear any screaming in the background, it's just my son. He's kind of being rambunctious today. Anyway, so what we have is, this is a reflection. We see how when I flip this guy over the y-axis, the before and after is still going to be congruent. So if I label this guy, this distance is 3, this distance is 3, this is 5.66, and so is that, and this is 4.12, and so is that, right? So a reflection is an isometry. If we try to do a rotation, if I do a rotation, let's say I rotate this like this, however many, whatever, 70 degrees. Okay, so I rotate it. Okay, I check this guy out. This one also, 5.66, 3, 4.12, so we can see that it's still an isometry. Right? It's still an isometry. Rotating from here to here did not change the size and shape at all, just kind of rotated it. And then obviously as translation, if you took this guy and just slid it downward, is there an easy way to translate? So I take this guy, I translate it. I don't quite know how to do that. Okay, let's try that like that. So I slide it down. Translation. So I took this guy, I slid it downward. Oops. Ooh. Slid it downward. So this guy to this guy, and I check out the distance. It's still going to be 3, 4.12, 5.66, right? So a reflection, a rotation, a translation, they're all isometries. The before and after is just congruent, right? This is an isometry, an isometry, an isometry, which means the before and after are congruent, 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 right? Dilations was the only one that was different. And so when I take this shape and I blow it up or I shrink it down, that's where we come up with something new. So let me jump over here. So this GeoGebra shows a dilation. I took this red one and I blew it up. And now I can see, a little bit too much here, I can see the result. And so let me try and clear out some of these guys here. Okay. So what we can see is if I take this guy and I blow it up, and let me move the scale factor so you can see it. The scale factor was 2, so that means all the coordinates doubled. I don't know if you saw them, if you remember that, but the coordinates double. But what we see here is also, look at that, also this side, which was 3, right, a length of 3 became a length of 6. This side, length 5, became a length of 10, and so on and so forth. And so looking at the side lengths, let me just take the scale factor. Let me increase it to be 3. Just back up a little bit. So look, this is 3, now it became 9, this length. This is 5, its corresponding side is 15. And so you can kind of see where we're going with this. If the scale factor is 4, Well, 3 then became 12, 5 became 20. So what we can see is I take this and I can multiply by 4 to get the new side length. Or I can go backwards, do 12 divided by 3 gives me 4, 20 divided by 5 gives me 4 as well. Okay, so these dilations produced similar figures, right? They produced similar figures. So we can look at this as a definition. What is a similar figure going to do for me? Well, first off, the side lengths are going to be multiples of 4, or multiples of whatever the scale factor is. In fact, all of them are, right? I could take 12 divided by 3, that gives me 4. 20 divided by 5, that gives me 4. Let's check out some other ones real fast here. 12, so this must be 3, or 12 divided by 3 gives me 4. 14.44 is this guy. Let's check out this guy. It's kind of hard to see. What is that, 3.6? Let's divide 14.44 divided by 3.6. 14.44 divided by 3.6. Okay, so it's 4. Right, that's just because of the rounding. So in other words, the ratio of this to this is the same as this to this, is the ratio of this to this, this to this is all 4. And you could see it'd be the same thing if it was 5, right, or 3, or whatever, right? 9 divided by 3, 9 divided by 3, all 15 divided by 5, it's all the same. And remember, when the rates, or excuse me, the ratios are the same, we call that proportional. Proportional, okay? So part of our definition is, of similar figures, is the side lengths are proportional, okay? So actually, let's jump to page 1, our vocab sheet. Page 1, our vocab sheet. So, similar polygons, part of the definition. Come here to page 1, our vocab sheet. Similar polygons. Two polygons are similar if they're, let's jump to the second one, corresponding side lengths are proportional. Okay? So, in other words, like if this was a scale factor of 2, I'm not saying it is, like if this was 10, this was 5, this was 8, this was 4. In other words, 10 to 5 is the same ratio as 8 to 4, right? Proportional means it's the same fraction. This reduces to 2 to 1, this reduces to 2 to 1. So side lengths are proportional. Second thing, if we go back and look at this GeoGebra here, look at the angles. This corresponding angles are 90 degrees, this is 123.7, 56.3, and 90. And even if I go and I change this, so let me go ahead and just kind of open this up a little bit, make it kind of weird. If I go and look, okay, make it kind of weird, 93.3, yep, 93.3, 41.6, so on and so forth. So we can see that the corresponding angles are going to be congruent, right? So the angles are congruent, and the sides are proportional. That is our definition, all right? The angles are congruent, right? 120.9, 120.9, so on and so forth, and the sides are proportional. So let's write that. Similar polygons. Angles must be congruent, right? So you blew it up, and the shape stayed the same. So this angle B must be the same as this angle F. This angle A must be the same as this angle E. This angle C, arc, 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 must be the same as this angle G, and this angle D, arc, 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 is the same as this angle H, arc, 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 arc. Right, so the angles are congruent because it's the same thing, just blown up or shrunk down, and the sides are proportional. So this to this is not going to be the same, but 10 to 5 is the same ratio as 8 to 4. This to this is the same as this to this, is the same as this to this, right? If this was, I don't know, like, if this was 9, then this would have to be 4.5, right? 9 over 4.5. And this was 12, this would have to be 6. I'm just making the numbers up, right? So angles congruent, sides proportional. This we're actually going to more focus on the next lesson, but looking at dilations helped us to figure that out, right? Angles congruent and sides proportional. All right, so let's jump back to our notes. So what we see is which transformations of these 4 produced similar figures, right? Not translations, not reflections, not rotations. Those are all isometries. It's dilations, right? So basically we're focusing on dilations. We're making similar figures where the angles are congruent and the sides are proportional. And it's a lot of, this section is a lot of review from chapter 9, but let's go ahead and do it. All right, so let's go ahead and draw a dilation of quadrilateral ABCD with vertices A at 2, 1, okay, B at 4, 1, C at 4, -1, and D at 1, -1. Okay, and let me go ahead and use my library card here. And I might actually use a smaller pen here. Oops, sorry, that's a mistake. It should be right here. Sorry, this figure right here. Not that. Okay, so we're going to dilate it with a scale factor of 2. All right, so again, if you remember, the old way was we'd actually took a ruler, measured this distance, and then multiplied by 2 or whatever the scale factor was. But the quick way is, if I take A, 2, 1, if you remember, and I want to get A prime, I just multiply these by 2. So A prime is just going to be 4, 2, 4, 2. Okay, so let's go ahead and do that. 4, 2, that's A prime. B is 4, 1. So B prime is 8, 2. I'm just going to multiply by that scale factor. So it's 8, 2. C is 4, -1. And D is 1, -1. So C prime is 8, -2. And D prime is 2, -2. So 8, -2, and 2, -2. That, oops. Oh yeah, 2's over here. Excuse me. D. Okay, so if I draw that in, let's go ahead and finish this up. We can see the dilation occurred. We can just multiply by the scale factor. Again, the rule is if I have xy, I'm just going to multiply it by the scale factor, kx, ky. So why don't you go ahead and try number 2, pause the video, and just make sure you have the same answer with the scale factor, a reduction of 1/2. All right, so hopefully you've done this and you've seen we've taken this original ABC figure and we have reduced it, right? It's a reduction to form D, E, F. Okay, so hopefully we're able to do that from chapter 9. Now the second part is I'm interested in this is how do I verify that they are similar? We'll do more of this again in a second after this section, but again the definition is they're going to be similar if the angles are congruent and the sides are proportional. Right, this to this is the same as this to this, the same as this to this. In other words, they're all dilated by the same scale factor, which really should be happening here. So one kind of way that we could do that is to check the sides. Let's just count here. 1, 2, 3. This is length 3. 1, 2. This is length 2. I could use the distance formula here, but I'm not going to count that. This is just to kind of check here. If I count this, 1, 2, 3, 4. This is 4. Like this distance here, 1, 2, 3, 4, 5, 6. This is a distance of 6. And again, so what I see here is if I go and I divide 3 divided by 6, 3 to 6, that does indeed equal 2 to 4. 3 to 6, this to this is this to this. And if I calculate this length and this length, they would be a little bit probably fractional, but it would still be the exact same 1 to 2 ratio, right? The angles are congruent. You could measure it with the protractor, but suffice to say, this is not a proof, but yes, they are similar. So in other words, a dilation does indeed produce similar figures where the sides are proportional and the angles are congruent. Okay. Next, let's find the coordinates of LM and N so that triangle LMN is a dilation with a scale factor of K. Is it a reduction or an enlargement? So if I start with PQR with these coordinates, and let's say K is 0.4, go ahead and pause and see if you can find this. Since K is 0.4, I'll give that to you. Of course, we remember if it's less than 1 is a reduction, right? So it's going to get smaller than these coordinates. So go ahead and find that, please. All right, so remember the key is I want to take it for any dilation. All these I forgot to mention, you can assume that they were dilated in respect to the origin, right? The origin is your point of dilation, so we can indeed use this, kx, k times x, k times y. So 0.4 times x, 0.4 times y. So a couple ways you could do this. You could take 0.4, and 0.4 is really 4/10, right? It's 4/10. So you could write as 4/10. You could even reduce that, divide by 2 over 2. You could make it 2/5. So you could turn it into a fraction, 2/5, or you could just multiply by 0.4. If you don't have a calculator, just multiply by 4 and then just move the decimal back over again. Okay, so for example, P is going to map to L. So L is going to be 0.4 times 5 and 0.4 times -5, right? So what is 0.4 times 5? Well, just do 4 times 5, that's 20, and then move the decimal over 1. So 20, and then move the decimal over 1, so it's just 2, right? 2.0. And so 0.4 times -5 would be -2.0, or -2. Okay? If I'd use the fraction, that would also work. So if I did 2/5 times 5, right? 2/5 times 5 over 1. 2/5 times 5. 5 over 5 is just 1. I can just cross that out. I'm left with 2. Right? So either way, that works. Let's just do this as well. 10. So 10, 2/5 times 10. I could do 20 divided by 5, or I could just say 10 over 5 is the same as 2. 2 times 2 equals 4. Right? So I can use that fraction, or I could multiply 10 times 0.4, which is 10 times 4 is 40. Move the decimal over 1 and you get 4. Right? So in other words, Q mapped to M, so M is going to be 4, right? -5 mapped to -2, and R, right? 10, as we saw, maps to 4, and 5 maps to 2. So here are our new coordinates. We just multiply by the scale factor. You can multiply or change it to you multiply by the decimal, or change it to a fraction, whatever you want to do to get those new coordinates. All right, last 2 questions. So number 4, I want to create a quadrilateral EFGH that is similar to this quadrilateral PQRS. What is the coordinates of H? And so just like with the congruency, these guys are going to match up, right? E goes to P, F corresponds to Q, G corresponds to R, H corresponds to S, right? H corresponds to S. So the problem is, you see how H is kind of like off the page here? I don't quite know what is the coordinates of H. So see if you can figure it out. Pause the video, see if you can get it. Okay, so if you were having trouble, I want to create this to be similar to this. So if it was similar, remember the definition is, if it was similar, all the angles would be congruent, all the sides would be proportional. So all I'd have to do is find the scale factor. How much am I blowing up the blue to get to the red? Now I can't tell from S to H because H is off the page, but if I look at P, look at P's coordinates here. P is what, 3, 0, and P goes to E. Was that 1, 2, 3, 4, 5, 6, 7, 8, 9? E is 9, 0. Okay, or if maybe you looked at R, R is 0, 2. 0, 2 became 1, 2, 3, 4, 5, 6. 0, 6. And so whether you look from 2 to 6 or from 3 to 9, you can see that our scale factor K is 3, right? We are tripling it, right? You're tripling the coordinates. And so because everything is proportional to getting dilated in the same scale factor, let's just find this coordinate right here. 1, 2, 3, 4. So S is 4, 1, 2, 3, 4, 5. S is 4, 5. If I apply that exact same scale factor, 4 times 3, so H must be 12. And then 5 times 3 is 15. So H must be 12, 15. So choice C is our answer. Okay, last one. So this is really leading us to where we're going afterwards, using similar triangles and polygons. So let's find the scale factor from A to B. Figure A to B, then give the unknown lengths. Okay, is it a reduction or an enlargement? Okay, since I'm getting larger, I guess it's an enlargement. So our scale factor is going to be greater than 1. So for the scale factor, I could either pick this over this or this over this, because again, it doesn't matter which one I choose. This to this should be the same ratio as this to this, because remember, all the sides are proportional. It's getting blown up by the same amount. So we're going to pick the image over the pre-image, right? So I'm guessing my scale factor is 8/5. Let me just check to see what decimal that is. 8/5. 8/5. 8 divided by 5. 1.6. Okay, 1.6. And that makes sense. It's an enlargement. Now, what if I had chosen this one, though? What if I had chosen 9.6 over 6? Let's check that on the calculator. 9.6 over 6. Oh, yeah, it's the same. That makes sense, right? It should be the same because this to this is the same as this to this. Hold on one second. I gotta pause. And so we could use either one, obviously, and we could just make a proportion. So to find x, a few things I could do. I could use 8 to 5. So this to this is the same as, and so this guy, 12.8, is going to go with x. So I could say this to this is the same as 12.8 is to x. I could have used this one. I could say 9.6 to 6 is the same as 12.8 is to x. Or, since we already calculated the scale factor, we know that 8/5 is just 1.6. So maybe an even easier way is just to say 8/5, that's just 1.6. So that equals 12.8 over x. And so it doesn't really matter. You could cross multiply this. So if I do this problem, I get 8x equals, let's see, 12.8 times 5. So 12 times 5 is 60. 0.8 times 5, well, 8 times 5 is 40, so that'd be 4. So this would be 64. So if I divide by 8, it looks like x equals 8 here. If I do this one, I would get 9.6x equals, let's see, 12 times 6 is 72. 6 times 8 is 48. So 6 times 0.8 would be 4.8. So 72 plus 4.8, 76.8. Divide both by 9.6. So let's just do that here on the calculator. 76.8 divided by 9.6. Oh, yes, that's also 8. And if you did it this way, you would just multiply both sides by x. Right? So you get x over here. And then we just divide both sides by 1.6. So 12.8 divided by 1.6. Oops. 12.8 divided by 1.6. And yes, our answer is 8 no matter what. Okay, that is the end of our lesson. We are getting ready to work with similar triangles, similar polygons. Go ahead and practice.